Okay, here we go. All right, so we're on the last section of notes for Unit 2. And then the rest of this week we're going to review. So first thing we're going to cover today is called function notation. And function notation is something that's kind of new to you guys. You didn't do very much of this last year. So really pay attention. It's not that hard, it's just kind of weird. So hopefully this will make sense when I explain it. First of all, let's define it. Function. Function notation. Function notation is another name for y. And it's written as f parentheses x. And you'll hear me call it f of x because parentheses mean multiply and the word of means multiply. That's what most teachers will say is f of x. Okay, so f parentheses x and read as the value of the function at x. The value of the function at x is what it actually kind of means. Basically, it's just like a formal way to write the letter y. Kind of like my friends that know me, they call me Stephanie because that's my first name. But you guys know me as Mrs. Reaper. Well, that Mrs. Reaper part is a little more formal. And Mrs. tells you immediately that what?
You're in charge.
That I'm married. That I'm in charge. That's awesome. But I'm also married, okay? Mrs. means I'm married. All right, so function notation. If you ever see f of x, so like here's a plain basic way to write a function. But if you see f of x, then there's no doubt that's a function. They can't write it in function notation if it's not a function. So, you know those questions where it was asking you to decide if it was a function or not a function? If it's written like this, you know it's a function. That's just like the Mrs. means that I'm married. You know that I'm married. Okay, it's just a fancy way of writing the y. F of x is the same as y. X is still just x. But f of x, the whole thing, means y. Okay, so for instance, if they say f of x equals x minus 3, they might ask you a question like, what is f of 5? So it's really just a really weird way to write some of this stuff. So first of all, f of x means what? This whole thing is the same as
y.
Y. So this is the same as y equals x minus 3. And then over here, they stuck a 5 in for what letter?
X.
For x. So they're saying, what is the y number if the x number is 5 using this particular function? How would I figure that out?
You like plug in.
You just plug it in. So you're just going to stick the 5 right here. And 5 minus 3 equals?
2.
That's what the y number is when x is 5. So f of 5 is 2. You're just plugging it in. So it's not hard, it's just a weird way to write it. Like it's a weird way to ask the question. So if I asked you what is f of 10, what would it be? 7, because 10 minus 3 is 7. Or f of 7. That'd be 4, because 7 minus 3 is 4. Okay, you see what we're doing? We're just plugging them in. Okay, then sometimes they go backwards and they'll do this. Question. What is x when f of x equals 10?
13.
How'd you figure that out?
Because you said it's backwards.
It is backwards.
Oh, so
Okay, so f of x means, what does f of x mean?
why?
Y, so this is, if y is 10, what is x? So now what am I gonna do?
So, like,
Because he got it right, 13 is right.
Okay.
I'm gonna put that 10 in for
why?
y, so this is gonna end up being 10 equals
Equals
x
x
minus
minus
3.
three.
And how do you solve that?
Then you,
Just solve it like an
add
equation.
Add 3 to both sides, x equals 13. Okay, now this is a really easy one. It doesn't have very much going on in this function, which is nice. But I just kind of want you to see that they could ask it either way. They could ask you what is the x value when the y value is 10. But instead of using the word or the letter y, they're using f of x. Or they could ask you what is the x value, what is the y value when x equals a number. Okay, they could also do it without an actual function rule. Like this is a rule already. But what if they just give you a list of points? I guess that should be equals. So my list of points is 2, 1, -1, 0, 6, 3, and 3, 2. 2, 1, -1, 0, 6, 3, and 3, 2. There's my function. So instead of giving you a function rule where you can plug numbers in and get answers, they're giving you specific points. Okay, so this one's a discrete function. The first one is going to be a continuous function. Okay, what if they do this and they ask, well, what is f of 3? What variable did I plug that 3 in for?
For the x.
For the x. So I'm looking for the answer when x is 3,
So it'd be 3.
what is the y? So which one of those has x for 3? Has a 3 for x?
6 and 3.
No, that's the other way around. 3, 2 is the one that has the 3 on the x, right? Because this one's x, this one's y. So if the x is 3, what's the y?
2.
That's all.
That's it. Don't overthink it. Don't try to plug some number into something random because you don't have a rule. All you have is a list of points. So then they'll also ask it backwards. So what is x
For y.
when f of x equals 1?
It'd be 6, 2.
When f of x equals 1.
Or 2.
So which one has an f of x of 1?
B2. Wouldn't it?
2.
The only one that has y and has a 1 in the y spot is this one right here. So x is going to equal 2 on that one also. Because this is asking you when y is 1, what is the x number? And the top one is asking you when x is 3, what is the y number? Okay, that's function notation. So it's really not difficult, it's just kind of weird and different. It's just a different way to write it. Are there any questions on that stuff? Today we're just kind of finishing up. We're going to do categorizing functions next. Okay, so next we're going to categorize functions. So we've already done this a little bit, but we're going to add to it. We've already done discrete and continuous, right? We talked about you could look at a graph or you could look at a function and decide if it was discrete or continuous. Yes? Okay, just making sure you're with me. All right, we've already done those two. That's 2 ways to categorize a function. We're going to talk about a couple other ways today. The first 2 are super easy, and they just kind of make sense. You can have increasing functions. What is something increases? What does that mean?
But it means goes up.
It goes up. That's what this does. Goes up. From left to right. So if you're looking at a graph, the graph is going to go up from left to right. That would be an increasing function. Now, some functions can increase, but they can also decrease. So decreasing is the other one. So decreasing goes down from left to right. Increasing goes up, decreasing goes down. And then I need one vocabulary word to add to it. This isn't a way to categorize a function, but it's vocab that you need to know. And I really think you guys already know these, but we're going to put intercept down here just to make sure you know what this is. An intercept is where
it crosses the Y.
where the graph touches or crosses an axis. And the word intercept has the same root word as like interception in football. And I don't know if you know that much about football, but an interception in football is when the quarterback throws a pass and the defender gets to the pass, crosses the pathway of the football before the person who is supposed to get it. Right? Now in football there's some rules that I have to actually catch it or else it's not considered an interception. But the idea is that it's crossing the pathway of something. Okay? So that's why this is called the intercept. It's crossing the path of the axis, either the x-axis or the y-axis. All right, that's what it's doing. So that's kind of how that name came about. Like I said, in football, there's a little bit more to it. You have to actually catch the ball or else it's not considered an interception. All right, take one of your little graphs and glue it down here at the bottom. Take one of your graphs and glue it down at the bottom. We're just going to draw a picture or function type thing on this graph, and we're going to label it. Once you get it glued down, draw a function that kind of looks like this. It doesn't have to match mine exactly. It doesn't have to cross in the same places or anything like that. It's going to go up. Down, and then go back up. And I'm going to put arrows in again. Okay, would you say this is a continuous function or a discrete function?
Discrete. Oh, no, it's just continuous.
It's continuous because the lines are all connected, right? So discrete would be if it was a bunch of dots. This one's continuous, so we can go ahead and label it as continuous. Is it increasing or decreasing? Both. We need to label the sections, okay? So this one, this first little section right here, that's increasing. And this last little section right here is also increasing. And then the middle section is going down, so that one's going to be decreasing. The only other thing we're going to label are the intercepts. So how many x-intercepts does this one have?
3.
2.
3. Has 3. So it has one here. Now it depends. Yours may only have 2 because it may not have crossed back up across it. Mine has 3. So these are x-intercepts. It's hard to see. Those are supposed to be in green. And then, how many y-intercepts does it have?
It has what?
Just y-intercept. That's just labeling it. You should be able to look at any graph and tell if it's continuous or discrete, and be able to tell if it's increasing or decreasing, and if it's both, then kind of label where. Those two things you should be able to figure out pretty easily. All right, any questions on those? Intercepts okay and all that stuff, you understand that? All right, last little part we're going to do is called function families. This is also a way to categorize them. I'm going to write it way up here because I'm going to try to squeeze it all in on one page, but we'll see. I've not been successful so far because I write so big. But so function families. Function families. The first thing you need to know about function families is that there are these things called parent functions. And I don't know if y'all did parent functions last year.
Yeah, I did.
You did? Maybe it just depends on the teacher or where you were, which school you're at. Okay, so a parent function is the most basic function and graph of that family type. The most basic function and graph of that family type. And we're just going to look at 3 different types. The parents are the most basic, most boring, simplified, you know, just probably like what you think your parents are. Okay, so just think of the parents as the most basic ones. I don't know, you may have really cool parents. Okay, so we have 3 types we're going to talk about here in Algebra 1. There are plenty of other types of function families, okay, but you don't have to know them all. We're just doing 3. So the first type is linear. You should definitely recognize linear functions. I know you did lots of these last year. Linear functions. And go ahead and take one of your graphs and you can glue it right underneath that. Okay, so linear functions, the graph of a linear function, do you recognize the root word maybe that's in the word linear?
Line.
Line. That tells you what kind of graph it's going to have. Okay, so the graph is a line. Just a plain, straight, single line. That's a linear graph. That's a linear function. Okay, if it goes up and down, that's not a linear function like the one that we drew. That's several different linear functions, but only like one side of it would be a linear function. The parent function is what we're going to graph, and it's also the equation that I'm going to give you. So the parent function is y equals x. Most basic, most simple function of the linear functions. So if that's the case, if the y number and the x number equal, and I say x is 0, what is y going to be?
0.
0, so that's 0, 0. What if x is 1? The y is also 1. What if x is 2? Then y is 2. And so on and so on. And if you've got your ID badge, they make really easy straight edges for these little graphs. They're like the perfect size. So just lean down and connect the line. If you're not wearing your ID badge, shame on you. Get that thing around your neck. Okay. Yeah. You're stuck inside your jacket. Okay, so this is the parent function. That's what the parent function looks like. Now, that doesn't mean that every single line is going to be angled that same direction. Some of them go this way, some of them are flatter, some of them are steeper. Okay, but any line is going to go in this family. They won't all look exactly the same, but kind of. All right, there's a big hint so that you can know if it's a linear function or not. And the hint is the rate is always constant. The rate is always constant. I don't know how many times your teacher probably said last year, constant rate of change. But my guess is you heard that a few times. Something about a constant rate of change. Okay, in order for it to be a line, the rate of change has to be constant. The rate is always constant. Okay, so I need you to find the word problem that says a horticulturist for the nursery and florist division. That one. And we're going to glue it right down here. It's going to overlap the graph a little bit, but that's okay. We don't need that space. Just glue it right here. The horticulturist. Fun word to try to say.
Horticulture.
Basically a scientist that deals with plants. A farmer / scientist. Kind of what a horticulturist is. Okay, so a horticulturist, I'm going to read it for you. A horticulturist for the nursery and florist division of the ADA is collecting data to analyze the longevity, that means how long they last, of petals on a new species of daisy. So it's like a super important job he has here. He's like counting how long the daisy petals last. I'm sure that's a highly important job. That way they can have better daisies for the florist that last longer and blah, blah, blah. Okay, the test plant begins with 30 petals. He notes that each day the daisy drops 2 petals. So the first day, how many petals does it drop? 2. And the second day, how many petals does it drop? 2. And the third day, how many? 2. And so on, and so on, and so on. Since that's the same, each day it drops 2 petals. The rate is constant. Constant. At 2 petals, can't write on this little edge, per day. So it's dropping 2 petals per day. That's a constant rate. Okay?
Oh, yeah, like if a shirt costs $2 and every time you buy a shirt, it's $2.
That's a constant rate. So that makes a linear function, yes. So if it's the same every single time, the rate is the same. That tells you immediately this is a linear function. Okay, second family. It's going to be quadratic. Everybody have that written down?
Yeah.
Okay, I'll leave that little bottom part.
I'm getting the restroom.
I need your little slip that I gave you. Okay, quadratic functions is next. And you're going to glue a graph underneath there. Quadratic functions.
Or the X instead of the Q.
Okay, the graph of a quadratic function is called a parabola. We've seen some of these. Not parabola, even though that's what it looks like. Parabola. It's U-shaped. It's a U-shaped graph called a parabola. Okay, and you can remember that it's U-shaped because Q in the English language is always followed by U every single time. Queen, quack, quilt, quiet, all those words. Quail, equation, like any of that stuff. It always has Q and then U. The only time in English that it's not like that is if it's a proper name and somebody spelled the name that way and they left the U out.
Can't they just call it
So it's a U-shaped graph. I don't know why they didn't, but they named it a parabola. I don't know how they came up with that word. Huh? I don't know. I'm not sure why they came up with such a weird name. Maybe that was somebody's name back then and they wanted something named after them mathematically and that's what they did. I don't know. But here is the parent function. The parent function is y equals x squared. Y equals x squared. So if the x is 0, what is 0 squared? Still 0. So 0, 0 would be that point. The x is 1, what is 1 squared? Still 1, right? But here's where it gets different. So it almost looks like it's going to be linear, but then, what if x is 2? What is 2 squared? 4. So go over to 2 and up to 4. What if x is 3? What is 3 squared?
6.
No. 9. There we go. 3, 9. So you end up with this U-shaped graph like this. Because if I do negatives, it ends up doing the same thing. So it's going to look kind of like that. That's the parent function. Now it could be flipped upside down, and it would still be a quadratic as long as it was a U-shaped graph. It could be skinnier, it could be fatter, it could be whatever. But as long as it kind of makes it U-shaped, then that is a quadratic function. So hence, hint is if it's a problem about area, it's going to be quadratic. Because when I do area, length times width, my units were always units what?
Squared.
Squared. And since this has a little x squared right here, that's a hint. Anytime you have anything with area, it's going to be a quadratic graph. Okay, so area, if anything is thrown, kicked, dropped, or shot, those are all going to be quadratic functions. And I'm going to explain that in just a sec. So the two word problems I said keep together. One is a football and the other one is the length of a rectangle. Those two go with this one. And they can overlap the graph a little bit too. Don't cover up your parent function. And maybe I might be able to actually, looky there, I'm going to be able to fit them. This is the first time. I haven't been able to fit them all on one. All right, so I'll go up here and do it on this one. All right, so on this one, a football kicked up in the air. And this is the reason why thrown, kicked, drop, shot. Actually, let's look at the rectangle first. Length of a rectangle is 7 meters more than the width. The area is 60 square meters. That right there is your clue that it's going to be a quadratic. If it deals with area or square units, it's going to be a graph that looks like this. Okay, so that's your hint on the second one. But the first one is a football is kicked up into the air with an initial upward velocity of 25 meters per second and then blah, blah, blah. Okay, that sounds like real complicated, but I just want you to think about, here's the grass, the football's going to go up, and then it's going to come back down. Something like that. Okay, they've learned in physics that anytime you kick, throw, or shoot something, or drop something like off of a building or whatever, it's going to have the same kind of a curve every single time. They call it trajectory. So it's going to go up, and it's going to come back down, and this side of the arch is going to be the same as that side of the arch, which is kind of weird, but it just is. It's just how it works. Okay? So this is going to be a quadratic function, even though it's upside down. It's still a U-shaped graph, kind of like a rainbow. So, and if you think about, if anybody has done any archery or maybe shooting long-distance rifles or anything like that, and if you're trying to aim for a target, you have to aim up above. Like, you can't aim straight and hit the target, I mean, unless you're, like, really close. But if you're long distance and you're shooting a bow and arrow, that arrow has to be aimed a little bit higher than what you're trying to hit. Because it's going to go up and then it's going to come back down. If you're in outdoor adventures, you guys are going to do that. Okay, so you're gonna have all kinds of bruises on your arms because you're gonna release that bow. Outdoor adventures. Okay, it's kind of fun actually. Anyway, that's what that is. It's a quadratic function, and if you ever take physics, that's kind of some of the stuff you learn is how to figure out, like, well, where's it gonna land then? If I hit it this hard, or I kicked it this hard, or I shot with this much force, where's it gonna land? And how far up is it gonna go, and all that kind of stuff. It's a pretty interesting course. All right, let me erase that. But that's how you know that both of those are quadratics. All right, last function family.
America.
Last function family is called exponential. Exponential functions, and then glue your last graph under that.
How long have you been teaching high school, Ms. Reed?
This is my 11th year for algebra. Exponential functions. And this one's kind of weird. We don't use this one very much, but you have to be able to recognize it. Okay, we're going to use it some. You have to be able to figure out domain and range and things like that. So you have to kind of recognize it. The graph curves just slightly. And never touches the boundary line, and I'll have to explain that in just a sec. It curves slightly and never touches the boundary line. And the parent function looks like this. It's y equals b to the x power. Okay, and the b just represents any number that you decide to put in there, or that they decide in your problem to put in there. Okay, so the parent function is y equals b to the x power. The reason it's called exponential is because where is the variable x? It's the exponent, okay? That's why it's called exponential. Okay, the graph looks like this. It's going to start up top and it's going to curve down and it's going to look like it's getting closer and closer to the x-axis but never quite touch it. Okay, I can't draw it perfectly where it's going to continue to get closer and closer and closer because there's just no way. I'm not that great and my pen doesn't get that skinny and whatever. I can't draw infinity. But it's kind of like if you started at the back wall back there and I said take one step, really big step, and then the next step take a step half that size, and then the next step take a step half that size, and so on and so on. How long would it take you to get up to this front?
Probably about 2 hours.
Maybe. Would you
take a huge step.
Would you ever actually make it all the way to the front? Think about it. Technically. Now your physical body would, because there's no way to cut in half. Like if your step is this big, teeny tiny, and you cut that in half, how are you going to step like that? Like there's no way. You know what I mean? You physically aren't going to be able to do that. But could I still cut it in half? And could I still cut it in half again?
Yeah.
And cut it in half again? And get some crazy like decimals? Yes. Would I ever actually reach 0 by cutting something in half? No. So I'd never actually technically, mathematically make it to the board. Now physically I probably would because there's no way I could step like that. Like there's no way I could step 0.000001 of an inch or something like that. That'd be impossible. Okay? So that's what an exponential does. It goes toward a boundary line but never ever actually reaches it. Now the trick is, when you look at it, one of these in your calculator, if you have a calculator, go to y equals. and clear whatever's in there. I don't remember what I had to put in there. But do 2 to the x power. So it looks like this, 2 to the x power. Okay, just type that in. And then hit the graph button. And it's way up at the top right corner. Bless you.
Let's see.
Okay, do y'all see how it looks like it just ends right here? Right? It just looks like it stops.
Yeah.
It really doesn't just stop right there. But the calculator cannot physically draw that. Like it can't keep making it look like it's getting closer and closer and closer. There's no way for the calculator to do that. So if you're ever asked domain and range on one of these, you got to be really careful because domain, this goes on forever even though it doesn't look like it does. So what would be the domain of this? Is it going to keep getting wider and wider and wider? So domain would be what? All real numbers. You can't measure that domain. It's going to go on and on forever. It's all real numbers. Range, however, never goes below that 0. So it's going to be everything above 0. Everything above 0 for range. But domain is going to be all real numbers. Even though it looks like it stops, technically there's no way for it to stop. The calculator just, I mean, the graphics on these calculators aren't good anyway, but they're definitely not good enough to try to show infinity. All right, so I want you to make sure you kind of understand that. All right, hence, you'll deal a lot with exponential in biology, because if you're talking about bacteria or growth or decay or something called a half-life, that's how they measure how old things are. Okay, half-life. Or outside of biology, if you're ever doing interest, like compound interest or savings accounts or anything like that, those are all going to be exponential. So those all go with this biology one. We're going to glue this one down.
Sorry.
Okay, and I didn't have room on the little hints. If you have room, you can write down on there somewhere if the numbers get really, really large really fast or get really, really small really fast. Like if you end up with like teeny tiny crazy decimals in four numbers for the domain and your range ends up being these tiny decimals. Or if they get to be like in the tens of thousands after 4. Around behind there. So either one of those, if the numbers get really large or numbers get really small really fast, that tells you that it's exponential also. This one says the biologist for the Center of Disease Control is collecting data to analyze the growth patterns of a new species of bacteria. Right there you've got some pretty big hints that this one's going to be exponential. She begins with a petri dish and she knows each day the number of bacteria doubles. So it's going to get really big really fast. Because even if I only started out with 30 and then suddenly I have 60 and then suddenly I have 120 just in 3 days. And so then the next, I mean, it's going to get really big really fast. So it's going to be that kind of a weird curve. So those are the function families, the 3 that we need to know.
That's only 3.
This thing takes forever to turn off.